Creating a view. Often, you will create complex queries that will join and filter data from one or more tables. If you will routinely use the results of such queries, we recommend creating a view. A view is a database instance that looks much like a data table, except that this is not a real table. It is, rather, a result of an SQL query. Before we start working on views, we will demonstrate a feature of the SQL Server called Query Execution Plan. At first, we will create a select query in our S&P 500 database. This query will use average function and list average stock prices in each business sector. The query will include only companies with stock prices greater than 100. Before we execute the query, let's take a look at the execution plan. For that, we should select the query of interest and click the Display Estimated Execution Plan at the menu bar or press the Ctrl+L key. The result window at the bottom will show a scheme. The sequence shows the execution plan for the select query. Below each icon, the SQL Server Management Studio shows estimated time in percent of executing each operation or the cost of the operation. This functionality will be especially useful if you will be working with large data sets and complex queries. Knowing the estimated execution plan, data practitioners can rewrite the query and make it more cost-effective. However, we showed the estimation plan for another reason. Now, let's execute the query, ensure that it generates the result we expected, and create a view from this query. We will use the Create View command and name the view Top Sector Average. To see the list of the views in your database, we can expand the database tree in the Object Explorer window and find the branch named Views. Now let's write a query for retrieving all data from this view and see its estimated execution plan. For that, we select the query and click on the Display Estimated Execution Plan button. Note that the estimated execution plan for this simple query is exactly the same as for the source query we used to create the view. The reason is the nature of views. Views are not real tables, but rather virtual tables. When we created the view, no data were copied or moved. The data still exists in the same table. We only created an alias for the query. Now let's delete this view with the drop view command and create another one. Although the views are virtual tables, the importance of views for some applications like data warehouse is so high that the question of data retrieval performance becomes increasingly important. In this query, we select several columns from the source table and apply the filter. The resulting dataset has unique ticker values in each row. Now, we will create a view from this query and then create an index for this view. Indices can improve the query performance and, as a result, improve performance of views. We will call this view Incorporated, since it will let us view only the companies with the abbreviation Inc. in the name. Since we know that we are going to create an index for this view, we will bind this view to our schema called DBO. For that, we will use the keyword schema binding in the create view command and place the source table name in the square brackets with the database schema as the prefix. Let's select all data from this view to ensure that it is all set. Now we can create the index. We will use the create index command with the keywords unique and clustered. The first index for the view has to be clustered index. We will create the index on the column ticker in the view named Incorporated. The new index will be stored in the database under the same schema as the view. Now, all select operations with the indexed view will perform much faster than the query we used as the source for the view. You will note the performance improvement when you are working with large data sets. To delete the index, we can use the drop index command. Note that we should indicate the name of the view as the prefix for the index name. Finally, we can delete the view using the drop view command. Deleting the view is not the same as deleting the table. After the view is deleted, all our data will remain safe and untouched. Grouping and ordering. Grouping and ordering data sets is very easy with SQL. Let's see how this can be done on the examples. With the clause order by stock price, we can order the results by the stock price in ascending order. If we want to be explicit, which is always recommended, we can add a keyword ASC to indicate the sorting goes in ascending order. We can order the records by the stock price in descending order by using the keyword DESC in the order by clause. SQL can also sort by string variables. For example, we can sort our data set by the company name. With the keyword DESC, the sorting will be in reverse alphabetical order. The first rows in the resulting data set will have company names which start with the letter Z. Use of an ASC keyword will sort the results in regular alphabetical order from A to Z. In SQL, grouping is also straightforward. In this query, we will calculate average stock price by sector. For that, we will use the group by clause with the sector variable. One thing we should mention here is that the select statement should only have the variable that you are using in the group by clause. In other words, if you will try to select sector variable and the company name from the table, the query will generate an error since the company name variable is not in the group by clause. Lastly, we will show how to perform filtering on the grouping results. For that, we will use the having clause. The having clause is like the where clause we use in filters, except the having clause can filter the results of grouping. Here, the query will return the list of business sectors and the average company stock prices in each sector sorted in ascending order. Note that because of the having filter, the resulting set includes only stock prices greater than 100. Partitioning. One of the greatest things that SQL can do with the data is automatically creating subsets of data and performing calculations on it. The function that can create subsets or partitions of data is called partitioning. The command that tells SQL to perform calculations over the subsets is called the keyword over. Combined, the function is called over partitioning. We will demonstrate how to calculate average on the subset of data. Count the number of records in the subset, calculate rank of the record, show the row number, and split the data into a fixed number of subsets or tiles. Before we start, we will recall how we calculated average in our previous examples. For that, we used the average function with the group by clause. The limitation for this query structure is restriction on the list of columns in the select query. We cannot list other table columns in the query like this. The overPartition function removed this limitation. We can construct a query with the list of the table columns, calculate average stock price in each sector, and display it as the calculated column. This query tells the SQL server that we want to calculate average stock price on the dataset partitioned by the sector variable. The records with the same value as the sector variable will form a separate data subset or partition. Now we will count how many companies are in each sector. For that, we will use the count function with the over partition clause. Note that we use the keyword distinct to avoid repetition. Since SQL attempts to show the count values for each company name in the table, we do not need this. We also want to sort the results by the number of companies in each sector in descending order. For that, we use the order by clause with DESC abbreviation. Next, we will calculate rank of each company in each sector by its stock price. The SQL function rank will serve our needs. The following query tells SQL Server to partition the data set by the sector variable values, sort the companies in each sector by the value of the stock price, and assign a corresponding rank to each record. The company with the lowest stock price in the sector will have the rank of 1. The following company with slightly higher stock price will have the rank of 2, and so on. The highest rank will have the company with the highest stock price in the sector. If the two companies have the same stock price, then they will have equal ranks. In a similar table, we can generate replacing the rank function with the row number function. In this query, the companies are sorted by the stock price values in each partition. The row number function returns the place of the record in the partition. The difference with the rank function is that if the two companies have the same stock price values, then its row numbers will be different, while the rank functions will return equal values. SQL has a function called entile. This function can split the data set into a fixed number of subsets. The number of subsets is the integer argument of the entile function. Sometimes you may need to split your data into several bins or tiles. For that, you can use the entile function with the partition clause. In this example, we will split companies in each sector into 4 subsets or 4 tiles. As you can see, the 4 subsets has seemingly equal number of records with each sector. However, this is not exactly so. The entile function does not always split the records into the equally sized tiles. They are about the same, but not strictly equal. Unfortunately, we cannot control the exact number of records in each tile with the entile function. That is why we recommend checking the size of each subset before using the results. To see the actual size of each file, we can create one more query on top of the query with the entile. In this complex query, we will select data from the partitioned dataset and count the number of companies in each tile. As we can see from the query results, the entile function split the dataset into about equal tiles, but not of the same size. Use the entile function with caution. Date and Time, Part 1. We talked about how to work with numeric and character data formats. With SQL, it was relatively simple. However, when it comes to data and time, there is no single recipe. The challenge is in variety of possible data formats. In your work, you may meet date records in various styles and languages. We will show you how to import the date and time records into the SQL tables and deal with the variety of styles. SQL has 2 main data types to work with date and time. These data formats are called date and time. Very natural. But we recommend importing your date and time records as strings. After that, you can attempt to recognize the correct date and time format and convert the strings to date and time data types. For the data type conversion, the SQL Server has several functions. The cast function is the most common SQL function. With cast, you can convert between all major SQL data types: numeric, character, and dates. The convert function is similar to cast. The only major difference is that with convert, you can specify the style of the date format when converting from strings to dates. Most likely, you will never need the style option in your data science work. Parse is the most advanced function for converting strings to dates. It can understand most date formats. Be aware that parse is not a native SQL function. You have to have a .NET framework installed on your machine to make the parse function work. Parse is a function of the Microsoft .NET platform that you can seamlessly run on your SQL server. If your servers are remote, then quite possibly the parse function will not work. So use parse with caution if your SQL scripts will work in a production environment. The three more functions, try cast, try convert, and try parse, are the same as cast, convert, and parse, except that it will not throw errors if the conversion will fail. Instead, these try versions of the function will silently return null values and will not stop the SQL execution. To demonstrate how to convert strings to the date format, we will create a table in our S&P 500 database. The table will have only one column in varchar data type. We will populate the column with strings containing dates in various formats. Let's check that the table is populated with the data as expected. Now we construct a select query with three functions, try cast, try convert, and try parse. These functions will attempt to convert our records into the date format. After the query is executed, we can examine the results of conversion of each function. We can see that the try-cast and try-convert functions performed equally successfully and failed on the same records. The try-parse function did the better job. It managed to convert all records to the date format correctly, except the last one. Fortunately, the parse function has an option to change the date regional settings, or culture, in the terms of the .NET framework. In the new select query, we will indicate that the records should be treated as if it came from Finland. For that, we set the try parse to use the Finnish style of date recording. As we see from the resulting table, the try parse function correctly recognized the last record and converted it to the date format. However, now it does not recognize some dates recorded in a format that is not used in Finland. In your data science work, you may need to vary regions and converting functions to enable correct date conversion. To help you with that, we included culture codes for various languages that you can use with the using command in the parse and try parse functions. If you will be using the parse function a lot, you will notice that it is not as fast as other SQL functions. Part of the reason is that parse is not a native SQL function. To improve performance, you can copy your select statement results into a new table. With that, you will have to convert dates only once, and then just retrieve the converted data from the table you created. You can create a new table with the select into command. The command is much like the standard select statement, except that you indicate a name of a new table where you want to copy the results of the query. The SQL server will automatically create the table and copy the results. Selecting from the new table will be much faster. You will notice the performance improvement when you will be working with large data sets. Date and time, Part 2. As you saw, converting date and time is not something that can always be done with a routine procedure. Now we will introduce one more converting function that is native to the date and time formatting called datePart. But we will not stop here. We will move one step ahead and explain how string functions like ltrim, substring, and concat can help when all-over conversion functions fail. To start, we will create a table with a string column and fill it with time records in the string format. As we said before, we recommend you start working with date and time records with the string format and then convert it into date and time. The string records that we insert have three sets of numbers, each separated with a colon. It stands for hours, minutes, and dates. We intentionally placed leading and trailing spaces around the digits. In real-life records, we will meet all kinds of formats and obstacles. Now we will convert the string records into time format with the try-parse function. As you see from the resulting table, the parsing function did its job well and converted the strings into the time format. With the date part function, we can extract information about hours, minutes, and seconds. For that, we will apply the date part function to the results of conversion and use the appropriate keywords, hour, minute, and second. The result of this query is a table with three columns that contain information about hours, minutes, and seconds. There are more keywords that you can use with the date part function to get even deeper insight into the date and time records. So, we successfully extracted the information on time from our string records. But what if the parse function fails or is not available? We will show you how you can parse the string with the means of the SQL string functions. At first, we will use the ltrim function to cut out the leading spaces in our records. If we would like to cut out trailing spaces, then we use the rtrim function. Since we know that our records have three sets of digits divided with a colon, and each set stands for hours, minutes, and seconds, we can extract these three parts with the substring function and call it hours, minutes, and seconds in the string format. The substring function takes three arguments: the name of the string variable, the starting position of the substring, and the length of the substring. We can see from the resulting table that our string parsing process works. Now let's create the true time variable from the results of our string parsing efforts. At first, we will concatenate the strings with information about hours, minutes, and seconds. But the concatenated string should also have a colon as the separator. That will help to convert it to the time format. So we construct a nested query where we get the inputs to the concat function from the previously created select query. Finally, we need to convert the concatenated string into the time format. We can do that with the convert function. As we can see from the query result, the conversion was a success. Now you know how to convert your date and time records into the date and time format and use it in your data analysis work.